Okay, so in this example problem, we're going to be solving for the velocity of a solid sphere by the time it reaches the bottom of an inclined plane if it rolls without slipping. And all it means to roll without slipping is that the sphere actually rolls down the hill and doesn't slide down like if it were icy, for example. So assuming it rolls down the hill, how fast will it be going by the time it reaches the bottom? I've included an LOL diagram on this slide because what I'm starting to realize is I have a complex set of energies here. As the sphere goes down the hill, it's going to have translational kinetic energy because it will be moving linearly through space, but it will also be rotating, right? It'll also have an angular velocity, so it's also going to have rotational kinetic energy. And because the sphere is some distance above the ground, we'll call that y, it's also going to have gravitational potential energy. And so as the sphere rolls down the hill, all three forms of this energy will be changing constantly. And because of the complexity of this situation, I want to draw an LOL diagram to help me analyze the different forms of energy initially and finally. I'm going to assume my initial state here as the sphere is at the top of the hill and it is not moving, so it's not quite yet moving. And my final state will be at the bottom of the hill while it is in motion. I will also take a moment, as I've defined my initial and final positions, to define the system. I will include the sphere in my system as well as the Earth. And I want to include the Earth because if I don't include the Earth, I can't talk about gravitational potential energy. I have to include the Earth to have gravitational potential energy. So in my initial state, is there any translational kinetic energy? And the answer is no, there's not. I'm not looking at the point when it's moving. I'm looking at the point when right where it's been released, it is not yet moving. And so there's no translational or rotational kinetic energy. However, there is gravitational potential energy because the sphere is above the ground. And I'll just assume there are 4 bars of gravitational potential energy. Totally arbitrary. I'm just going to pick 4. Okay. Now, I know there's no work being done on the sphere because I'm ignoring friction here, and I don't see any external forces or torques. Because gravity is an internal force here, because my Earth is in my system, that's not an external force. And so my work here is 0. So I'll just say the work is equal to 0. There's no work here being done. Okay. So I already know that my gravitational potential energy is the total energy, right? I never get any more than I had at the beginning. Some of it becomes translational, some of it becomes rotational. And so by the time the sphere gets to the bottom, I'm going to have both of these, right? I'm going to have translational and rotational kinetic energy, but I will not have gravitational potential energy, okay? And once again, that's because the sphere is both moving linearly through space, but also rotating or rolling. And so I'm just going to arbitrarily I'll just show, let's say, I don't know, if I had 4 bars of gravitational potential earlier, I'm going to guess and say, you know what, maybe they're equal, right? I'm just going to say 2 and 2 right here. Not that that necessarily indicates that they're equal, but relatively I have some translational and some rotational kinetic energy. Okay, so my formula, this is the reason we draw the LOL diagram, is the gravitational potential at point A, if I call the top of the hill point A, will be equal to the translational kinetic energy at point B plus the rotational kinetic energy at point B. This is my energy conservation equation that I can use now to solve for the velocity of the sphere at the bottom of the hill because I know that V is in here somewhere and indirectly also in the rotational kinetic energy formula, which we'll see in a moment. I've gone ahead and rewritten my conservation equation on the right-hand side, and I'll go ahead and begin by breaking each term down using the formulas for potential and kinetic energy, respectively, because I'm not given any of these values directly and I want the velocity, so I'm going to go ahead and break each of these down. All right, so I've expanded each of these terms and I've dropped the subscripts of A and B because I'm only dealing with one height and one velocity here, so I don't need to really keep track of different velocities and different heights. Now, I would just rearrange this equation for V right now, but I also know that omega is related to V, the velocity of the sphere. And so what I'd like to do is break this down as far as I can go. And I know from my bridge equations that the linear velocity of an object that is rolling is equal to the radius of that object multiplied by the angular acceleration of that object, right? That's one of our 3 bridge equations. And so, in other words, right, if you rearrange this for omega by dividing both sides by r, right, then you will get that omega equals v over r. Or in other words, the angular velocity of an object is the linear velocity of that object divided by its radius. And so I can plug this in to this equation. So I can say omega equals v over r, just plug that in right here for omega to further break this equation down. That would look like this. All right. Now, since that omega was being squared, the v over r is being squared. And so if I square v over r, then my expression would look something like this. All right. Now, I also noticed that there's a mass in two of my terms here. And when we've solved problems like this before in the past, mass has canceled. And so I'm wondering if I can do the same thing here to make this a bit simpler to work with. Well, I know that the moment of inertia, I, is actually equal to what for a solid sphere? Well, for a solid sphere, I is 2/5 times the mass of the sphere times the radius of the sphere squared. And so there's actually an m inside of that I term. And so I'm going to plug this in for I instead of I and see what happens to my equation then. So that would look like this. All right, and so now that I've plugged in my moment of inertia formula right there, I notice that I can start canceling some quantities out, right? There's a mass in each of these terms. There's a mass here, here, and this is all one term, right? This everything after this plus sign here. So there's a mass in here as well. I can cancel the mass because it appears in each term. I can cancel my masses. I can factor it out basically of both sides, and that would go away. And because there's an r squared here up high, and there's an r squared here down low, those will cancel. R squared divided by r squared will just give me 1. And so that term will actually go away as well. So that leaves me with an expression that looks like this now. All right, and so I see the 1/2 here is from the energy formula, but the 2/5 here, this was that moment of inertia constant. Okay, I still have this 2/5 sticking around, but now my equation looks almost the same on the right side. I have something v squared plus something times v squared. So I'm just going to multiply 1/2 by 2/5 to combine those v squared terms. All right, when you multiply fractions together, you multiply the numerators across and the denominators across. And now in order to add the two v squared terms here, I'm going to change 1/2 it to 5/10 because that's the same thing as 1/2. 5/10 is the same thing as 1/2. That would give me g times y is equal to 7/10 times v squared, so the 5/10 plus 2/10. And then now I can finally go ahead and rearrange here for v. All right, and if I do that, I'm going to multiply both sides by 10/7, or the reciprocal of 7/10 to get rid of that on the side with the v squared. So that would be 10/7 times g times y is v squared. Take the square root of both sides. The velocity of the sphere, the linear velocity of the sphere at the bottom of the inclined plane, is the square root of 10/7 multiplied by g, our acceleration due to gravity on Earth, and the height of the sphere y. And so I want you to notice here that the velocity of the sphere is dependent on 3 things, right? Number 1, it's dependent on g. So on Earth, that's a constant, but on different planets, right, that would affect the velocity of the sphere at the bottom of the inclined plane differently. The second factor that affects the velocity of the sphere at the bottom of the hill is y, the height that the ball was initially released from. If we release the ball from a higher height, it's going to have a larger velocity by the time it gets to the bottom of the inclined plane, and that should make sense. Now, the third thing that may be less obvious is the shape of the object, and I want to point out where that's coming from. If you look at the equation for the velocity that we just derived here, this 10/7 quantity, that came in part from the moment of inertia, right? The moment of inertia, that constant 2/5 that came with the moment of inertia for a sphere, became that 10/7 term, that it influenced that term, right? And so the shape of the object will influence the velocity of that object by the time it reaches the bottom of the inclined plane. Now, I'd like you to compare what we just did here with what we did many times in this class so far, and that was for a box sliding down an inclined plane. There's a reason we haven't looked at rolling objects yet in this class, and that's because we weren't able to account for this extra form of rotational kinetic energy. And so if I bring up the equation once again for a box, if you just have potential energy being converted into purely translational kinetic energy, you'll remember that the velocity of the box at the bottom of the inclined plane was equal to 2 times g times y. And so you'll see here that 2, right, 2 is bigger than 10 over 7. So what this is telling you is that the box has a greater velocity by the time it reaches the bottom of the inclined plane. And that should make sense, hopefully, right? If the box and the sphere both start at the top of the hill, they're going to have the same amount of gravitational potential energy. By the time each of them gets to the bottom of the hill, the box still has all of that energy as translational kinetic energy, but the sphere has given up some of that translational kinetic energy in order to rotate. And so rotating objects don't travel as fast linearly because they're using some of that energy to rotate. And we can prove that mathematically here by deriving the equations for the velocity of the objects at the bottom of the inclined plane. But we can also understand that conceptually because we only have so much energy to start with. And the more places we put that energy, right? If I put some in rotational kinetic energy and some in translational kinetic energy, I'm not going to have as much in either one as if I've transferred all of it to either purely translational or purely rotational. Let's take a look and see if we can apply what we just learned here to a previous example that we've seen already.